Hello everyone, welcome to 10-Minute Physiology. In today's video, I'm going to be giving you a short explanation of the middle ear, so with that, let's give it a go. So I would like to begin by first giving you a short explanation of the anatomy of our ear. So the first part of the ear we'll look at is a part called the pinna. So the pinna is basically part of your outer ear, and its function is to reflect sound waves into a specific canal called the external auditory canal. Now, the external auditory canal then funnels sound waves to the tympanic membrane or the eardrum. This then brings us into the middle ear. So in the middle ear, we basically have three bones called ossicles, and each of these bones has a specific name. The first one is the malleus, the second is the incus, and the third is the stapes. And we're going to talk about the function of these bones in this video today. This then brings us into the inner ear. And the inner ear is basically where all the action is going to be taking place. So this is where the auditory and vestibular systems are basically going to be generating signals that are then brought into the central nervous system. Now, the main structure that you should worry about in the inner ear is going to be the cochlea. So the cochlea has a number of important parts. The first are the semicircular canals, which are responsible for measuring acceleration. So these are going to be very important for your vestibular system. In addition, we also have the ampullae. Now, the ampullae are these enlarged bases at each of the semicircular canals, and this is basically where acceleration is going to be measured in these canals. In addition to these structures, we also have the round window, and covered by the stapes, we have the oval window. And those are going to be the main important parts for the cochlea. Now, the next important part to the ear is going to be the eustachian tube. So the eustachian tube is going to be responsible for equalizing pressure inside our ears. And then the last important part is going to be cranial nerve number 8, which basically takes information from both the vestibular and auditory systems into the central nervous system for processing. So these are going to be the most important parts that you should know for the ear. So now that we know that, let's talk about the function of the middle ear. But before we talk about the function of the middle ear, we're going to talk about a specific concept called acoustic impedance. So with that, let's talk about what this is. So what is acoustic impedance? So acoustic impedance basically describes how hard it is to vibrate something with a pressure wave. So it's the tendency of a medium to oppose movement brought upon by a pressure wave. Now, sound is a pressure wave. So imagine that you have water. So you have air on top of the surface of the water and water below the surface. So let's just say you take some sound waves and aim them at the surface of the water. So what would happen? Well, in order to understand what would happen, we have to know the acoustic impedance of each medium. Now, the acoustic impedance of air is low. This means it's very easy to vibrate the molecules in the air, whereas the acoustic impedance is high in the water, and this means that it's harder to vibrate these molecules. So when pressure waves basically travel from an area of low acoustic impedance to an area of high acoustic impedance, what happens is the majority of the energy that is carried by these pressure waves will be reflected off the surface of the media with the higher acoustic impedance. So as a result, around 97% of the sound's energy is reflected off the surface of the water. And this is because water has a higher acoustic impedance than air. So in order to sense sound, the energy that is transferred by the sound waves, which originates in air, must be transferred into the fluid in our ears. Now, the fluid in our ears is basically water, so this presents us a problem. How is the sound wave supposed to transfer its energy from an area of low acoustic impedance, so from air, to an area of high acoustic impedance, such as the fluid in our ears, without most of these sound waves being reflected off the surface? So in order to answer that, we're going to do a little demonstration. So imagine you have a big window, and this window we'll call window 1. Now, attached to this window, we have 3 levers, and these levers are basically all attached to one another. Now, the third lever, the pink lever, is going to be adjacent to a tank full of water. And the area where the lever basically touches the tank of water is another window that's able to vibrate. And we'll call this window window 2. So let's see what happens when we expose this system to sound waves. So when we basically expose the system to sound waves, and these sound waves are originating from air, what happens is the pressure waves carry energy, and this energy is absorbed by oval window 1. As a result, the oval window will vibrate. So what can we do with this oval window 1? Well, one thing that we can do is basically bring in a specific concept called intensity. So intensity is equal to the amount of energy per unit area. So it's basically telling you how much energy is dispersed over a certain area. So let's just say that the energy that the window absorbed from the sound waves is equal to 10 units. And let's just say that the area is equal to 5 meters squared. So the intensity is equal to 2 units per meter squared. And this intensity would basically correlate to how strong the vibrations of this window are. So basically, the higher the intensity, the stronger the vibrations. So then what would happen? Well, all of the energy that was absorbed by oval window 1 would be transferred into the lever system. And the lever system would actually be able to transfer the grand majority of energy that the oval 1 window basically absorbed. So it's important to realize that most of the energy, 10 units, is transmitted to the smaller window that we see right here through this lever system. And actually what happens is that the lever system is actually going to amplify the pressure of the wave. So then this brings us to the smaller window that is outside the tank. So what would happen at this smaller window? Well, all of the energy that was basically absorbed by this window is now being transferred to this window. So we have 10 units of energy that was transferred all the way from oval 1 to this smaller window. So in order to understand what happens, we have to calculate the intensity. So let's note that the area of this window is a lot smaller than window 1. In fact, it's around 100 times smaller in this case. So what we do is we basically take the amount of energy, so 10 units, because all of that was transferred to this window, and divide it by the new area. And what we get is an intensity equal to 200 units per meter squared. So this intensity is 100 times larger than the intensity that was experienced in this window. So as a result, the vibrations of this window are going to be much larger than the vibrations experienced by oval window 1. And this is because the intensity here is larger. So it's because of these more forceful and greater movements that we can basically transfer the energy into the fluid and cause vibrations in the fluid. So once again, because of the smaller surface area, the intensity of the pressure wave is amplified even though the amount of energy is the same. So in other words, both the lever system and the smaller sized oval window amplify the pressure of the wave. This allows most of the energy to be successfully transferred to the liquid in the box. And in fact, this is the type of mechanism that is used by our middle ears to transfer energy. So if we looked at the lever system in our body, you would notice that it's very similar to the one that we just talked about. So basically, the big oval window 1 is now correlated to the tympanic membrane. And the 3 levers are the malleus, the incus, and the stapes. And the small window that was on that tank of fluid is correlated to the oval window. And what we have here is the cochlea. There are 2 regions of the cochlea, the scala vestibuli and the scala tympani. And basically these are filled with fluid. So the cochlea is going to be correlated to the water tank. So it's in order to get the waves from the air into the fluid in our ears, our body uses a lever system formed by the malleus, incus, and stapes. The lever system and the much smaller surface area of the oval window, which is in fact 20-fold smaller than the tympanic membrane, amplify the pressure of the sound waves. This allows most of the energy to be transferred to the liquids of the inner ear. So it's because of this lever system and the usage of surface area that we can transfer the energy from the air into the fluid in our ears. So the last thing that I would talk about is what basically happens in our inner ear during a sound wave. And if you saw my previous video, there's basically 2 phases in a sound wave. The first is the compression phase, where the molecules are really close together. And then there is the refractory phase, which is when they're far apart. So what happens in the compression phase? Well, in the compression phase of the sound wave, what basically happens is the tympanic membrane is basically pushed inward. As a result, this causes the movement of the lever system in the following directions. And as a result, the stapes basically pushes into the oval window, which basically causes fluid to flow from the oval window all the way to the round window here. So this is basically what's going to happen in the middle ear when you have the compression phase. So what about the rarefaction phase? So in the rarefaction phase, basically what's going to happen is that the tympanic membrane is going to be pulled out. As a result of this is going to cause the opposite movement of everything that we just saw. So the lever system is going to move this way. The stapes is going to move this way, pulling the fluid all the way from the round window to the oval window. So we basically have the opposite effects. So I hope this video helped you understand the middle ear, and I hope to see you in the next video. Thank you for watching, and I hope to see you next time.